Hello, this is part 3. How to present your data. Presenting your data in table form is usually not good enough because only those set of numbers is not as good as showing them in a graphical way. But once you get to the graphical way, some way are better than the others, and that is visualization basics. So to make sure you know how to present the data, we need to talk about visualization channel ranking. And then finally, we'll introduce the Box-Whisker or box plot. We will illustrate this part with many examples. And finally, there are 3 recommended books. They are not academic textbook. So this part is how to present your data. The easiest way, a table. Here is a table. We see the p-value of Anderson-Darling test, mean value, a standard deviation, variance, skewness, kurtosis, minimum, Q1, median, and so on. So reading this table with a whole lot of numbers usually is not very easy to quickly grasp the idea for what you're going to talk about. Therefore, we need to know how to present the data. And here is a list of visualization basics. How to present your data visually requires the understanding of some elements. First of all, human perceptual system has 2 fundamentally different kinds of sensory modalities. They are the identity channel and the magnitude channel. The identity channels tell us information about what something is or where it is. For example, the identity channels may include circle, triangles, colors, motion, inside, outside of an area, and so on and so forth. So we use identity channels to identify what it is and where it is. The magnitude channels tell us how much of something there is. For example, longer versus shorter, larger versus smaller, brighter versus darker. And we have 2 principles, the expressiveness principle and the effectiveness principle. Let's talk about visualization expressiveness. The expressiveness example states that the visual encoding, that is your graphics should express all of and only the information in the dataset attribute. In other words, your graphics must say everything available in the dataset, and you can only say those things in the dataset. You should not add, you should not miss something. So order the data like a numerical value, say body weight measurement. These are ordered data, should be shown in a way that our perceptual system senses as ordered. Unordered data should not be shown in a way that perceptually implies an ordering. The identity channels are the correct match for unordered categorical attribute. What does that mean by categorical attribute? For example, animal categories or pets categories, cats, dogs, and so on. And the magnitude of channels are good matches for ordered attribute or ordinal and quantitative attribute, because there is a way for us to say this one is larger than the other one. The visualization effectiveness. The effectiveness principle states that the importance of the attribute should match with the salience or noticeability of the channel. The most important attribute in your data set should be encoded with the most effective channels in order to be most noticeable. Less important attributes can be matched with less effective channel. Then you will ask a question. Which channels are more effective than the others? Good question. Before we get into that part, let's say, never ever misrepresent your data. So here is a grade and percentage of a class. A has 21%, AB has 23%, and so on. The failed one, 11%. We want to draw a graph or a chart to present this data. So line chart is pretty good. A 21, AB 23, and the B 14, and so on. So we see immediately we have A, the highest will be AB, the lowest will be the D. In this case, a line chart are very frequently used. But when you use line chart, scale is usually a very tricky issue. For an example, you use a very narrow scale. Then the same line chart looks very flat, nearly has no fluctuation, unlike this one. Or if you want to present your graph here, but you don't have enough space, so you squeeze the line chart, squeeze their x-coordinate, then this line chart looks way too sharp. So among these three, this one is a natural one. This one is way too flat, and this one is way too sharp. So both of these failed to show the differences properly. So when you use line chart, the scale for you to draw the line chart is a very tricky one. Now look at this. The top row actually shows the same data set. It shows that the height in inches of female, the height in inch for male, collect from a study. So this is a categorical. Male height would be here. The male height is here between 50 to 60. And the female height is a bit shorter. Two group, male and a female. This is a bar chart. Now, if you convert it to a line chart, so that is female has this high, male has this high. You use a line chart. You may feel that something is wrong. Yes, if you have that feeling, you are good. Because when you draw a line chart has a natural trending indicating going in this way. So many people would read this line chart as follows. The more male a person is, the taller he or she is. So we implied a trend out of a data set that does not have a trend. So if your data is discrete rather than discontinuous, it would be much better to use bar chart. 10 years old, height, 12 years old height. So in this case, if you use a line chart, it means height increases with age. So remember this, line charts encourage trend assessment. Here, using a line chart may be okay, but for this one, it's definitely a misleading line chart. So don't add anything not in the data. Then we try to answer what kind of a channel would be better than the others. Now, the left side has those channels for magnitude channels. That is for order attribute. The right-hand side has the identity channels for categorical attributes. This diagram is taken from this textbook. So from top to bottom, these channels are listed as the most effective to the least effective. This list has psychological and recognition study. It's not a random chart. So for ordered attribute, the most effective channel is position on common scale. So we have two scales. Common scale same, and we are easy to compare. Okay, this one is larger than this one. The second most effective channel would be positions on unallied scale. We have two scale, unallied. This scale is shorter than this scale. Sometimes we are still able to compare, but sometimes we may have difficulty. Followed by length, one-dimensional, followed by angle, tilting. But the problem is people can easily recognize perpendicular and horizontal line and probably 40-degree line. But many people cannot distinguish 20-degree and 40-degree and probably 50-degree. So it's less effective. Area that is two-dimensional size. When you have two areas separated by some distance, it's very difficult to understand which one is larger than the other one. So depth, 3D position is even more difficult. Now, look at here, color luminance, the color, and the color saturation. They are at the same level. It's very difficult to distinguish between this color and that color, and this level of saturation with the other level of saturation. Curvature. People can easily recognize vertical line or straight line or a semicircle. But between that, sometimes it's very difficult for people to say this one is different from the other one. And finally, 3D volume is just an extension of the 2D size. So always remember, for showing magnitude channel, the most effective one would be position on common scale and the positions on unallied scale. The remaining one are not very effective. So these are the ranking for magnitude channel. Now take a look at the identity channel, space region. I put something at this corner, something at this corner, and something at this corner. So the position can easily be seen and recognized. Color hue, well, if your color hue is different, then it's also recognized. And motion is commonly used in, say, tablets for you to select something, followed by shape. You may want to say, hey, shape should be easily recognizable. unfortunately, is not. Triangle, circle, and the cross, these are maybe okay. But when you have polygons with many sides, it's not so easy. So as you can see, the topmost effective channels are positions and well, you can also say position on common scale. Spatial region is also a position. So spatial channels are the only ones that appear on both lists at the top. Spatial relation is also a spatial relation. None of the others are effective for both data types. The above channels are for 2D, and 3D depth is a much lower channel. So remember, when you want to present your graphics, make sure use the topmost channels in order to make your visualization very effective. So for the magnitude of the channel is a summary. The effectiveness order is position on common scale, position on unaligned scale, followed by length, followed by angle, followed by color, followed by curvature. Design graphics and the charts using the position on common or unaligned scale, as these two are the most noticeable for presenting order data. Now, the use of color sometimes can be risky. Color blindness is a sex-linked inherited trait that affects 8% of males and 0.5% of females. Out of 100 males, probably 8 of them may not be able to distinguish certain color effectively. And out of 1,000 females, probably 5 of them would have the same problem. A common form of color blindness is the ability to sense the red and green color axis is very limited or even absent. So use color carefully as it's not very effective. Return to our confidence interval example. Remember, we have 20 examples, 20 samples. This graph has all the confidence intervals on a common scale. So you can see this confidence interval is lower than this one, and this one is out of bound. And this confidence interval does not contain the population mean. So all of these 20 confidence intervals are on the same scale. So positions on common scale can easily help to see the differences between the ordered data set. Now, again, we use the grade and the percentage. The line charts and bar charts have a common scale. For each one has the common scale. This one is also use the common scale. So a line or bar chart fits our need perfectly. And that is why these two are very commonly used. But this line chart implies some ordering, which is okay because for A, followed by A, B, followed by B, and so on. But this is completely categorical. In this one, we consider 21%, 23% as an order set. But this one, we consider as a categorical, category A, category AB, and so on. Now, the pie chart is different from the line chart. Again, the same data set. Watch out for very thin slides, which can be difficult to see. In addition to that, remember area, the pie chart use area to indicate the size. So if you look at this pie chart, can you see the difference between A and AB, 21% and 23%? Can you see the difference between B and C? B is 14%, C is 11%. It's very difficult to see. And it's even more difficult to compare. Okay, I have D here. What's the differences between this D and CD and even BC? So a pie chart uses area. And area is not a very effective channel. There is a not so commonly seen graph called the radial, radar, or spider chart. It combines the line pie chart by doing this. Here are the x-axis. We pull all the x-axis together to become a point, which is the origin of this radial chart. And then we draw a polygon or a circle and spread these values onto this radius. For example, A is here. So A goes from the origin here, and this is a B, this is C, AB, and B, BC, and C. So even though the radial chart has all points on a scale radiating out, it is still difficult to read. For an example, just like we mentioned, okay, it's difficult to see how the difference is between two very similar values. Say BC, which is 8, CD is 9. But on here, you can easily see the differences, right? But here it's still difficult. Then let's talk about the Box-Whisker plot. Why we talk about here? Well, it simply tells you nearly everything we want. Remember, we talk about quartile and outlier. We compute minimum, maximum, first quartile Q1, and the second quartile, the median, and third quartile Q3. So we draw a line from minimum to maximum and mark Q1, median, and quartile Q3. And also we add the mean value. So we draw a box, a rectangle between Q1 and Q3. This box contains 50% of the data point. And we draw a line from minimum to first quartile, and a line from third quartile to maximum. These two line segments are referred to as whiskers. A box plot can be horizontal or vertical, and many box plots can be shown in a single graph. Many systems also show individual data points and the outliers. Here is an example. We draw a box between Q1 and Q3, and we mark the median Q2 here. We also put mean value here. So the length of this box is the IQR, interquartile range. We draw a line segment from the minimum to first quartile, and also a line segment from Q3 to maximum. These two are whiskers. As I mentioned, some system may draw those data points on this line segment. So the IQR is used to determine outliers. Let's take a look at examples. Example 1. Remember, we have a teaching evaluation data set available on the supplied Excel file. So this is the box plot. Minimum, which is 1. Q1 is 2. Median is 4. Mean is 3.4. And the maximum is 5. So we don't have the right whisker. We do have left whisker. So from the minimum to Q1, we have 25%. And from Q2 to the median, we have another 25%. But Q3 is equal to maximum. Therefore, from Q3 to maximum, we have 50%. As a result, we mentioned the use of mean is misleading, is a poor decision. Remember that anger is perhaps the cause of low rating. So assess this with more evidence. Example 2, we have in data exam score 5 data set. This is the box plot for this data set. So let's try to explain the whole thing. We have minimum 4, Q1 31.5, and the median 48, Q3 65, maximum 82. And the mean value is 46.1. So close to the median. The confidence interval for mean is this. Confidence interval for median is, you could also draw the confidence interval here, but due to the graphic would be too busy, I did not put these two confidence interval in. Therefore, from this box plot, we learned that about 50% of the students who participate in this exam has scores between 31.5 and 65. Not very well, but indeed we still have 25% students perform very well, and another 25% with some very low score. So this is a box plot. Now let's take a look at the histogram. The skewness is negative 0.44. The kurtosis is negative 0.72. Remember, in the last lecture, we did Anderson-Darling test. It returns a p-value of 0.034, which is less than 0.05. And the score distribution is not. We have evidence to show that the score is not normal. The kurtosis negative means it's rather flat, and the skewness is 0.44 negative, is not symmetric. So with a histogram and the computer data in the box plot, you should be able to have a rather comprehensive picture of the given data. Example 3, let's take a look at the programming average data. As we mentioned a couple times, students perform very well except for some unmotivated ones. Here is the box plot. Minimum is 10, Q1 is 67, median 86, Q3 97, maximum 100. The mean value is 74.53. So here, this portion is 75 students were good at programming, and we have outliers here. The lower 25% pulls down the mean value. Again, the use of mean in this case is misleading if the distribution is not bell-shaped, even though its skewness is close to 0. So whether you want to include these outliers for your study of the student performance is your choice. I would present 2 sets, one set without outliers, with some explanation why you exclude them. And then another set is all outliers are included. Now, look at the distribution. Skewness, negative 1.18. quite large. The kurtosis is not very large. However, the Anderson-Darling test shows P equals 0.005, very, very small. Therefore, we have strong evidence showing that this score distribution is not normal. Notice here we have 6 outliers. You could try by removing the 6 outliers, what you will get. A good exercise. Example 4. In an exam, there is a theoretical problem. Well, probably you know that computer science students are not very good at it, theoretical reasoning. But anyway, there is a theoretical problem in an exam, with maximum number of points is 10. The data set is here. Students did not perform well, and many gave up. That is, Q1 equals mean equals 0. But still, we had 25% of students perform very well. So 75% of students has their scores less than the 3rd quartile. Only 25% had their score in the 3rd quartile. Now let's look at the histogram. The lower 25%, a large number, dragged mean down. Again, the use of the mean is somewhat misleading. So again, if you want to study this, you could do 2. 1, remove the lowest one, 0, because they gave up, and see what you get. Notice here, these 0 are not outliers because they equal to the 1st quartile and also equals to the mean value. So here we present you 4 examples, each of which shows some characteristic. Let's give you a summary. A box plot uses positions on a common scale. This is the scale. We put a dot here and line here to indicate the position of that value. So the Box-Whiskers, Q1, median, Q3, and length, here the whiskers, and the IQRs. And we also use spatial region in this box. All of them are top rank, magnitude, and identity channels. And this is why we introduce to you the box plot at the end of this first set of lectures. It is a very powerful tool. In general, if you want to do an exploratory data analysis, usually we refer to it as EDA, better do this. So finally, as we mentioned so many times, when you should not use the mean value and you use it, you run the risk of misinterpreting your data, or sometimes you may even misleading people. So misinterpretation of your data, whether it's intentional or unintentional, could make your work unreliable and unconvincing. In 1954, a reporter, Huff, wrote a book, How to Lie with Statistics, in which he used so many examples taken from politicians and reporters. Maybe they unintentionally did something, and the result will be quite different if you interpret your data correctly. So do not misuse or abuse statistics. I recommend you to read the following 3 books, very easy to read, and probably also cheap. The first one is, of course, How to Lie with Statistics. The second one is How Charts Lies. Well, we talk about how to do your graphics, right? But you could also intentionally or unintentionally made some charts to lie. So this book is a very interesting book. Getting how charts lie, getting smarter about visual information. And then the third one is how to lie with maps. You may want to say, wait a minute, how can you lie with maps? Yes, you can do that. This book, the third edition, provides you so many such examples. So when you collect your data from your experiments or your project, even though today, this is the last slide of the descriptive statistic with one attribute, you still learn something. How to organize your data, how to present your data so that you will not mislead your user and will not add anything that is not in the data set. And you do not miss anything in the data set. Hopefully, you will be able to find some time to read this book, these 3 books. All 3 of them are worthwhile your time. Then that's the end of this descriptive statistic with one attribute. The next set of lectures would be on multi-attributes. So let me stop here today, and hopefully you'll come back to watch the second set. Goodbye and good luck.